Hi guys, welcome to the first lecture on electrodynamics. And for this lecture series, we'll be using Introduction to Electrodynamics by David J. Griffiths as our main reference. I recommend you to buy this book because it will really help you. This first lecture, by the way, will serve as an introduction to the rest of the lectures. I hope that after this lecture, you will get the feel of what is electromagnetism or electrodynamics is. What is electrodynamics? There are four realms of mechanics. First, that we have studied is classical mechanics. This is mostly formulated by Newton, and you deal with big objects with observable speeds, low speeds. And then when the object goes to fast speed, like speed near the speed of light, you invoke special relativity by Einstein. And then when you have uh, particles, small particles with low speeds, then that is described by quantum mechanics and mostly formulated by Bohr, Heisenberg, Schrödinger, and others. But if you have small particles and moving with faster speeds, like going to the speed of light or near the speed of light, then that is the dynamics is described by the quantum field theory, mostly formulated by Dirac, Pauli, Feynman, Swinger, and others. So again, Newtonian classical mechanics holds true for objects with low speeds but was found to be inadequate for objects moving near the speed of light. So special relativity had to be incorporated according to Einstein. For the size of objects comparable to atoms, classical mechanics will fail, and so quantum mechanics has to come in to describe their dynamics. And then of course, if you have very fast and very small objects, special relativity and quantum mechanics combine to form the relativistic quantum mechanics, also known as quantum field theory. In nature, there are four kinds of forces. The first one is the strong force, which holds protons, neutrons together in atomic nucleus. If you have an atom, like a hydrogen atom, you have a center of that atom is called the nucleus, which is composed of a proton. And then you have a revolving electron in a hydrogen atom. But if you have a heavier atom, the nucleus will be composed of a proton or protons and neutrons with electrons revolving around that nucleus. What holds the protons and the neutrons together inside the nucleus is the strong force. Electromagnetic force, on the other hand, which was discovered by Benjamin Franklin, Coulomb, Andre Marie Ampere, Michael Faraday, and others. And this is completed and compactly packaged by J.C. Maxwell. Electromagnetic force is the second in terms of order. This is the second to the strong force. This is very strong, but second to strong force. And examples of these are like the force between two charges, for example, or friction, Normal force, for example, are examples of electromagnetic force. The third one is the weak force. These forces can be observed in radioactive decay of particles. Like you have a bigger atom, like a uranium, it will decay to a smaller atom plus some radiation. Then you have the weakest force called the gravitational force. This is observable between two huge masses or concentration of matter, like planets and stars. This is hardly noticeable, like on Earth. We don't experience gravity, the force of gravity, that strong compared to electric force. But we know that whenever you throw something up, it will always go down back to Earth, and that is really caused by gravitational force. This force dominates the entire universe because the universe is composed of stellar bodies which are really heavy. And even gravitational force can bend light. Here are examples of electromagnetic force or EM force: friction, normal force, chemical forces, colliding forces. Those are examples of electromagnetic forces. According to people, this is an electromagnetic world since every force in everyday life except gravity is electromagnetic in nature. The electrical repulsion between two electrons is actually more than 1,000 times as large as their gravitational attraction. If you can imagine it, if atoms were held together by gravity, a single hydrogen atom would be much larger than our known universe. That's how strong electrical force is compared to gravity. There were attempts to unify all the forces: the strong force, the electromagnetic force, the weak forces, and the gravitational force. But only some of these were unified or combined. Before, electricity was electricity and magnetism was magnetism, but now we study electricity and magnetism together, and we call it electromagnetism. In the beginning, or in the early days, Ørsted noticed that an electric current could deflect a magnetic compass needle. So when you place a compass near a magnetic material, the compass will move. André-Marie Ampère postulated that all magnetic phenomena are due to electric charges in motion. And Michael Faraday discovered that a moving magnet generates an electric current, and speculated that light is also electrical in nature. However, it was J.C. Maxwell and Henry Lorentz, with all of the above observations and discoveries, concluded and packaged that electricity and magnetism were inextricably intertwined. Thus, we have now electromagnetism. Hertz said that a connection between light and electricity is now established. In every flame, in every luminous particle, we see an electrical process. Thus, the domain of electricity extends over the whole of nature. It even affects our selves intimately. We perceive that we possess an electrical organ called the eye. Einstein, in the early part of 20th century, dreamed of a further unification by combining gravity with electrodynamics. But he was not successful. Then, in the later part of the 20th century, in the 1960s, electric theory was successfully created by Glashow, Weinberg, and Salam. They all got Nobel Prize for this. They were able to combine weak forces and electromagnetic forces. And they're particle physicists. Field formulation of electrodynamics. Actually, conventionally, or if you can imagine it, the space around an electric charge is permeated by electric and magnetic fields. You have a charge, a steady charge. They will radiate or absorb fields. If the charge is like spherical in nature, they radiate radial or absorb fields in radial direction towards its center. And if it is spinning, magnetic fields are formed, and they are perpendicular to the electric field that they produce. These electric and magnetic fields are detected by a second charge. So if you place another charge near a charge point or particle, the second charge will experience a force from the second charge. The fields then transmit the influence from one charge to another, and this is through a mediating particle. These mediating particles are actually photons, sorry. So the fields are actually mediating the interaction between two charges. Now here's the thing. When a charge accelerates, a portion of its field detaches itself from the charge and travels off at the speed of light, carrying with it energy, momentum, and angular momentum. And this is called electromagnetic radiation. Electromagnetic radiation are the photons. Their particle counterpart are the photons. So it sums up to that it takes a charge to produce an electromagnetic field, and it takes another charge to detect that field. Electric charges comes in two kinds. There is positive and negative charges. This is purely convention. Positive and negative, because when you put them together in equal amounts, they cancel to zero. But if only one exists, If one is isolated, only the other one can be detected, but if the other one is placed very near to that, they cancel. The effect is cancelled. So their effects tend to cancel when they're together. So if positive Q and negative are at the same point, electrically it is the same as having no charge at all at that point. The same type of charges repel, while if you have two opposite sign charges, they attract. Another fact of about charge is it is conserved. It cannot be created nor destroyed. This is called the conservation of charges. There's what we call global conservation of charge of the universe. The charge of the universe is constant, doesn't change. But there's also local conservation of charge. Like for example, your house has a constant charge, or your area has a constant charge. If you get a charge outside, it will affect the charges of, say for example, a place in New York. It will lose some charge because you've gained some charge. So that's what we call global conservation of charge. But in your area you also have local conservation of charge. Charge is quantized. Electric charge comes only in discrete lumps or integer multiples of a basic unit of charge, E. So an electron has charge negative E, and a proton has a charge of positive E. That's why when you have a hydrogen atom which has a nucleus of a proton and an electron revolving around it, the total charge of that atom is 0. So here are the units. If you read different books, the one book may use an SI unit, another book may use a Gaussian unit, or a Heaviside Lorentz unit. So for SI units, you have the force is equal to 1 over 4 pi epsilon times the product of the two charges for Coulomb's law divided by the distance square between the two charges. That's for SI units. In this book that we're using, it always refers to the SI unit. Other units could be Gaussian. Some books use Gaussian units where the epsilon sub O is equal to 1 over 4 pi, such that they just write the force to be equal to the square root, the product of two charges divided by the distance square between them. Other books use Heaviside Lorentz units, and they write the force there to be just 1 over 4 pi times the product of the two charges divided by r square. Epsilon sub O in Heaviside Lorentz units is equal to 1. So this is our reference. We use the Introduction to Electrodynamics by David J. Griffiths, Prentice Hall International Incorporated. You can use any edition of this book. I highly recommend that you get a hold of this book. If you have resources, then buy this book. That's all for this introduction of our lecture series, and watch out for the next one.